Hello, and welcome to Laney Photography Department's presentation on digital resolution. Back in 1823 to 26, a gentleman by the name of Niepce in France created this first capture, the first successful capture of an image. This is essentially a very fine asphalt that was exposed for about 12-13 hours and then rinsed with oil of lavender to leave this impression. And this is read by computer, and this is how it was interpreted to give us an idea of what the first image was like. In a few years we moved on to silver-based image capture, which is what we used a lot for the last couple hundred years. In essence, we have a base. It could have been a piece of glass. And you have an emulsion on top of it, which is essentially jello and silver halide grains. These grains are receptive to light, and light takes a particular electron in this compound and raises it to a new valence level, which makes it receptive to certain kinds of chemistry. And through development, we end up with a negative. That is, the crystals that created silver make dark areas. Anything else that's not been developed can get rinsed out, and you can get some really nice images. This is a negative. It's the consequent positive. We have a picture of the eye, and the light travels through the pupil into the back in the retina. This is the macula, where the greatest density of sensors is. The light travels through the retina, through these particular layers of the retina, past these ganglion cells and these bipolar cells, into rods and cones. And cones are more sensitive to color, rods more sensitive to light in general, but not color, because there's only one type of rod, there are 3 types of cones. And this information gets pushed back into the optic nerve. So photons travel through here, they get recorded, whatever's left over that goes by gets absorbed in this pigment layer. It does not bounce back. So the acuity is pretty good. We have the greatest number of cones in the macula, and the fovea is in the middle of that. And so the greatest color and the greatest acuity that we can get with color is in the very center of our vision. And you go to the edges outside the center of the retina, and you can see all the cones and the rods in between. The rods are sensitive to dark and light. The cones are sensitive more to color. And so what you see is 7 to 10 million cones, 100 to 120 million rods, and those send signals to our brain, and we end up with vision. Here's a silicon chip with pixels on it. It's about 4,000 pixels tall by 6,000 pixels wide. You can imagine that's about an inch in length, how small those pixels are and how much detail they can capture. They're set up in a variety of ways. This particular Bayer mosaic has the green and red and blue. You notice the numerous greens. That's because our eyes are more sensitive to green. So we take advantage of that. Light goes into each pixel through a micro lens. Underneath the micro lens is a color filter. And that color filter will block out all light except for its own color. And the amount of that color hits the photodiode. Same here. Blocks out all the light except for this color. And this diode reads that. That all goes into the computer. The computer makes decisions about how to mix these to make the colors that will be seen. Pixels. This is an image that's 2100 pixels wide at the bottom. At that resolution, you can see a lot of detail in this image. If we use any number of programs, we just use Photoshop here, we can change the number of pixels used to create an image. We'll go from 2100 to 1000 pixels. This is fewer pixels. And as we go down in number of pixels, you're going to start to see some changes. Here's 500, and you're starting to see the edges get what they call zaggy. that is, you're starting to see the individual pixels, so that diagonal lines that go across the sort of checkerboard of pixels start to show their edges. You can see it really well right in here. Okay? You can see it really well right in here. Let's go down to 250 pixels, and all of a sudden you can actually see the pixels. And you can see why things get zaggy, because all these little square pixels don't make nice diagonal lines. Look at all that zagginess. And here we are at 125 pixels. Here we are at 2100. Here we are at 125. The more pixels, the finer the image. So let's take this image and we're going to scale it down to where it looks pretty good on the screen. Well, that's not very useful. But that said, you need fewer pixels on a screen to make a decent image than you have to have in a printing file. On the Mac, you need 72 dots per inch of resolution to get a nice look. On a PC, it's 96 pixels per inch, or it used to be called dots per inch in magazine days. And then for making prints, you can use 240 or 300 pixels per inch. And that's all about resolution. How many pixels you can get in an inch to render the images that you need well. Let's go in the other direction. It's kind of interesting. Here is an image that's 40 by 24 pixels. It looks pretty good. I know it's teeny weeny, but you can see there's like a hillside and there's like a rainbow and sort of a hump in there. But let's start with that information and make it bigger. Okay, so we're going to make that image, that 40 odd pixels, as big as the entire screen, and that's what it ends up looking like. I mean, it looks sort of like what we saw before. That looked a whole lot better. It was all small and teeny weeny and blending together, so it fooled us to looking good. But this is what it looks like when it's blown up. Let's pretend we're starting with this original information. Let's blow it up to 125. The computer's interpreting this stuff, and you're starting to see some weird stuff going on here. Some weird fringing. And even the color's a little bit odd. Let's go up to 250 pixels from the original small one. And that fringing gets even better, or worse, depending upon how you feel about it. You can see the colors start to bleed. Let's go up to 500. And you can see very, very clearly, still the pixels with still the fringing and some of the funny color artifacts. We'll make that small one even bigger at 1,000 pixels. And now you don't quite see the pixels, but you're seeing a lot of interpretation or interpolation artifacts from the computer. It's doing the best it can with the information it's giving you. It's trying to smooth things out, and it's doing a pretty good job, but the detail is awful. And here we are at 2,000. Here's 1,000. Here's 2,000. Here's 1,000. You can just start to see some pixels, and here's 2,000. You don't see any pixels. And it's nice and smooth, but the color is weird, and the fringing is really bad. This is what the image is supposed to look like. So, one of the things we can take away from this is you have to get the largest and cleanest exposure you possibly can. And from there, you can always go smaller to make the file sizes that you need. If you wanted to make an image for printing, you would make this at 2100 pixels. This is about a 5 by 7 printed. And it looks fantastic here. And the same here. This would make a larger print. It's a bit larger, a larger file. But we want to get the largest, the cleanest, the most precise exposure we possibly can with every capture, because once we start changing resolutions, things can look funny. And if you start small and go big, it looks real funny. And if you start big and go small, you can do pretty well, but once you get down to a certain point, you start seeing the pixels and it's useless. So this all goes into how we think about the images as we capture them, and how we think about them as we export them. Thank you very much for your kind attention.